Welcome to this presentation of the ACS Auto-Tension V-Belt Drive. We will cover a number of conversions from the slide base to ACS configurations. This was the first ACS application under 500 horsepower. It involved the conversion of three 30-horsepower centrifugal pump drives used for digester recirculation. One pump is typically on standby, while the others each run 40 minutes out of every hour, 24 starts per day. Reused existing guard, reduced belts from 3 strands to 2 strands, removed cooling water. The plant soon stopped their frequent checks on these pumps. The drives no longer threw belts, ran first unit for 12 months, then completed all 3 drives. This milling plant area contains 106 drives, powering roller mills on the next floor. Now, this arrangement replaces the conventional line shaft. There are approximately 450 belts powering the various machines. Note erratic belts. Thrown belts on standard drive. ACS drive, spring assembly oriented downward for easy access. This is the same milling plant, but here we converted a 250 horsepower high-pressure blower in the vacuum transfer system, output shaft at 2700 RPM. Now, this starting sequence was made on completion of conversion. The plant ran this unit for 12 months, then ordered 3 200 horsepower units for a similar application. Note the soft start timeout before reaching speed, when the motor goes to full torque, and the idler responds to resulting tight span stretch. No squealing. This is a demonstration of belt change on the ACS drive. Begin by adjusting the idler out of the direct belt path between the 2 power pulleys. Remove the old set of belts and install a new set. Adjust the idler back into contact with the belt and continue until the static spring length coincides with the amber end of the green band on the gauge. Install guard and start the drive. During the break-in period, the belts will grow in length at a decreasing rate. Adjust as needed. When belt length stabilizes, make a final adjustment to the spring length. This job included the conversion of 6 40-horsepower blowers on a gas-fired paper dryer with ambient temperatures to 450 degrees Fahrenheit. Now we have nothing but music. The whump and squealing have completely disappeared. Start ramp is still 8 seconds. The plant was so impressed by this application that they decided to try this idea on the 3-horsepower exhaust blowers on these same furnaces. We actually tried to talk them out of it. Why bother with 3 horsepower? Note oscillations in the slack span in this slow motion segment. After 4 months of operation of the first drive, the plant ordered the remaining 5 units. They were evidently right. Now this is a 1-year-old wastewater plant. Our scope involved 5 blowers pumping air into the clarifier to control biological oxygen levels. When this sequence began after working hours, by next morning, the crew would find a smoke-filled building with starting ramp at 15 seconds, serious noise, and melting belts. Note idler oscillations on starting. In spring 2007, the plant manager personally made a presentation on these drives to the Wisconsin Wastewater Operators Association. Here we make a short presentation on belt growth. With the possible exception of the gravity base configuration, all V-belt drives require periodic human intervention to maintain traction. What makes this necessary is belt growth, the slow but steady increase in belt length with use. The mechanic faces 2 issues here. First, what is the current status of drive tension? 2, when an adjustment is necessary, how much correction should he actually make? We will work with the ACS test unit using a 10-horsepower motor. Drive traction requires that the dynamic slack span tension not drop below a given value. A rod links the top of the loading spring directly to the idler position. The colored bands of the barber pole enable us to infer from the spring length whether the slack span tension is okay, too low, or too high. The pole is custom configured for each application, taking into account many factors. When the top of the spring is in the green band, the drive will handle the maximum design power at any stage of belt growth. Simulating belt growth in our test rig, we see that the idler moves into the belt path, taking up the added length. However, the spring force and thus the slack tension fall as the spring extends. We will ensure sufficient traction if we make a shortening adjustment to keep the spring out of the red band. We have just neutralized the effects of belt growth. In the real world, this amount of length increase would typically occur over a few months. We have put the considerable complexity of this situation into the design of the spring-loading assembly and its gauge, and given the observer a clear and simple indication of the correctness of tension. No more ambiguity. No more expensive surprises. ACS has delivered 22 jack shafts in the 600 to 1,000 horsepower range since 2001 to mines in Canada, Chile, Indonesia, U.S., Peru, and Australia. These units drive cone crushers. 12 of these were 1,000 horsepower machines shipped in 2007. The ship weight is 7,200 pounds. In tough applications such as this, the ACS drive yields the greatest reduction in machine forces. The ACS auto tension drive is particularly attractive in the following situations: high inertia applications, starting under load, or frequent starts, since the drive does not squeal or throw belts, clutches smoothly, and usually eliminates the need for a soft start. In long-running process applications where belt growth can shut down a conventional drive and the process itself, when a drive spends considerable time in standby mode, where the low static shaft loads relieve all drive components and eliminate the risk of Brinelling bearings, whenever downtime is unacceptable, and finally, when having to move and realign the motor is unduly awkward or difficult. Thank you for viewing this presentation of ACS belted drive products.